Now let's begin by understanding what the binary number system is. The binary number system is the language that every computer uses to store and process information. Unlike the decimal number system, which uses 10 digits from 0 to 9, binary uses only 2 digits. Those 2 digits are 0 and 1. Every piece of data inside a computer, whether it is text, a picture, a video, music, or a computer program, is ultimately represented using combinations of these 2 digits. But why do computers use only 0 and 1? The answer lies in the computer's hardware. Inside every computer are billions of tiny electronic switches called transistors. Each transistor has only 2 stable states. It can be OFF, represented by 0, or ON, represented by 1. Because computers naturally work with these 2 states, binary is the most efficient number system for digital devices. As we continue this lesson, you'll discover how these simple zeros and ones can represent every number that a computer needs to process. Now that we know what binary is, let's understand why it is called base 2. The word base tells us how many different digits a number system uses. For example, the decimal number system uses 10 digits from 0 to 9. That is why decimal is called base 10. Binary is much simpler. It uses only 2 digits. Those digits are 0 and 1. Every binary number is created using only these 2 digits. Because there are only 2 possible digits, the binary number system is called base 2. As you can see on the number line, binary starts with 0 and 1. After that, there are no more digits available. So instead of creating a new single digit, binary moves to the next place value. This is why the next binary number is 10, followed by 11, then 100, and so on. The important thing to remember is that base 2 does not mean there are only 2 numbers. It means there are only 2 digits that can be used to build every binary number. Understanding this simple idea will make it much easier to learn binary counting and binary conversions in the next parts of this lesson. Now you might be wondering why computers use binary instead of the decimal number system that we use every day. The answer lies in the way computers are built. Inside every computer are billions of tiny electronic switches called transistors. Each transistor has only 2 stable states. It can be OFF or it can be ON. These 2 states are easy to represent using binary digits. OFF is represented by 0, and ON is represented by 1. Because computer hardware naturally works with only these 2 states, using binary makes electronic circuits simple, reliable, and efficient. Imagine trying to build a computer that had to recognize 10 different electrical states for the decimal digits, from 0 to 9. That would make the hardware much more complex and far less reliable. Using just 2 states makes it much easier for computers to store, process, and transmit information accurately. This is why every modern computer, smartphone, game console, and digital device uses the binary number system at its core. So remember this key idea. Humans use base 10 because we have 10 digits. Computers use base 2 because their electronic circuits have only 2 stable states, OFF and ON. Now that we understand why binary is called base 2, let's learn how to count in binary. On the left, you can see the familiar decimal numbers from 0 to 5. On the right are their binary equivalents. Decimal 0 is written as binary 0. Decimal 1 is written as binary 1. At this point, we have used both binary digits, 0 and 1. So when we count the next number, we cannot create a new digit. Instead, we move to a new place value. That is why decimal 2 becomes binary 10. Decimal 3 becomes 11. Next, decimal 4 becomes 10, 0. And decimal 5 becomes 10, 1. Notice the pattern. Binary counting follows exactly the same place value concept as decimal. The only difference is that binary has only 2 digits, while decimal has 10. As the numbers become larger, binary numbers grow longer because new place values are added whenever all possible combinations have been used. Once you understand this pattern, reading and writing binary numbers becomes much easier. In the next lesson, we'll use this knowledge to convert numbers between decimal and binary. Now that we know how to count in binary, let's learn about binary place values. Just like the decimal number system uses place values based on the powers of 10, the binary number system uses place values based on the powers of 2. We always read binary place values from right to left. The rightmost position has a value of 1, which is 2 to the power of 0. The next position has a value of 2, or 2 to the power of 1. Then comes 4, which is 2 squared. Next is 8, or 2 to the power of 3. After that comes 16, followed by 32. Notice the pattern. Each place value is exactly twice the value of the position to its right. This is the foundation of the binary number system. Whenever you read or convert a binary number, these place values tell you the value of each digit. As the binary number becomes larger, the place values continue to double. For example, after 32 comes 64, then 128, and the pattern continues. Remember this sequence well: 1, 2, 4, 8, 16, 32, 64, and 128. Knowing these place values will make reading and converting binary numbers much easier in the next part of the lesson. Now let's take a closer look at the binary place values. Every position in a binary number has a fixed value. We always begin from the rightmost digit, because that is the smallest place value. The first position has a value of 1. The next position is 2. Then comes 4, followed by 8, 16, and 32. Notice the pattern. Each place value is exactly twice the value of the position to its right. This is because binary is based on the powers of 2. The values continue to grow as 1, 2, 4, 8, 16, 32, 64, 128, and so on. These place values are the key to reading binary numbers. For example, if the binary number is 10101, we only add the place values where the digit is 1. So we add 16 plus 4 plus 1. The result is 21 in decimal. Remember this important rule. Every binary position has a fixed place value, but you only include that value in the calculation when the digit is 1. Once you remember the sequence of place values, converting binary numbers to decimal becomes simple and straightforward. Now that we know the binary place values, let's learn how to convert a binary number into a decimal number. We'll use the binary number 1011 as our example. The first step is to write the binary place values underneath each digit. From left to right, the place values are 8, 4, 2, and 1. Next, look at each binary digit. If the digit is 1, include its place value in the calculation. If the digit is 0, its value is 0, so we do not include it. For this example, we have 1, 0, 1, and 1. So we add 8 plus 0 plus 2 plus 1. The total is 11. Therefore, the binary number 1011, written as 1011 base 2, is equal to 11, written as 11 base 10. Remember this simple rule. Write the place values underneath the binary number, then add only the place values where the digit is 1. If you follow these two steps every time, converting binary numbers to decimal becomes quick, accurate, and easy. Let's work through another example of converting a binary number into a decimal number. This time, our binary number is 11001, or 11001 base 2. The first step is to write the binary place values underneath each digit. From left to right, the place values are 16, 8, 4, 2, and 1. Now compare each binary digit with its corresponding place value. The first digit is 1, so we include 16. The second digit is also 1, so we include 8. The third digit is 0, so its value is 0. The fourth digit is 0, so its value is also 0. The final digit is 1, so we include 1. Now add together only the place values where the digit is 1. 16 plus 8 plus 0 plus 0 plus 1 equals 25. Therefore, the binary number 11001, written as 11001 base 2, is equal to 25, written as 25 base 10. This example demonstrates the same rule we use every time. Write the place values underneath the binary number, then add only the values where the binary digit is 1. With regular practice, you'll be able to convert binary numbers to decimal quickly and accurately. Binary is used in almost every digital device we use every day. Computers, smartphones, tablets, and smart TVs all process information using binary. Digital cameras store photos in binary, while video games use binary to control graphics, sounds, and gameplay. The internet and cloud servers use binary to send and store data around the world. Even modern artificial intelligence systems rely on binary to process information and make decisions. Although we see text, images, videos, and apps, computers understand everything as combinations of zeros and ones. That is why binary is the foundation of all modern digital technology. Is binary a programming language? The answer is false. Binary is not a programming language. It is a number system that computers use to represent and process data. Programming languages such as Python, Java, C# and JavaScript are written by programmers. These programs are then translated into binary so that computers can understand and execute them. So remember, binary is the language of computers, but it is not a programming language. Now let's learn the most important rule for reading binary numbers. If you remember this one rule, converting binary numbers into decimal will become much easier. The rule is very simple. Only add the place values where the binary digit is 1. If the binary digit is 0, you do not add that place value because it contributes nothing to the final answer. Let's apply this rule to the example shown on the screen. The binary number is 10101. The place values are 16, 8, 4, 2, and 1. Now let's examine each digit one by one. The first digit is 1, so we include the place value 16. The second digit is 0, so we ignore the place value 8. The third digit is 1, so we include the place value 4. The fourth digit is 0, so we ignore the place value 2. Finally, the last digit is 1, so we include the place value 1. Now we simply add the selected place values. 16 plus 4 plus 1 equals 21. Therefore, the binary number 10101 is equal to 21 in decimal. Think of each binary digit as a simple decision. A 1 means include this value. A 0 means do not include this value. You never change the place values. You simply decide whether to include each one based on whether the binary digit is 1 or 0. Once you understand this rule, you'll be able to read almost any binary number quickly and accurately.